Hello and welcome to a glass plate. We're going to consider laminar flow through a simple geometry. It is a wall on this side and air here. And we have a strip, a layer of liquid of a thickness d that is sitting on this wall. You could think of water, Newtonian liquid, high viscous liquid, but it is Newtonian. And we're going to consider this as being very long in that direction and very long in that direction. And we take, as usual, a steady state, Newtonian and laminar flow. And what I would like to know is what is the velocity profile of this liquid. Well, obviously, if it flows, it will come down. Because the driving force for this flow is gravity, pulling everything down. I assume that there is no pressure difference across this, so that the pressure is uniform everywhere. I know what to do. I need to set up a balance, a force balance, this geometry, over a piece out of the liquid and equate all the forces. And thus I need to define a coordinate system. And my coordinate system will be vertical y, horizontal x, starting at the wall. Okay, as usual, I start equating all forces. That is in principle shearing forces. So shear stress on the side, potential shear stress on the side here, a gravity. No pressure, because I assume that the pressures are equal. Of course there's something pressing here, but it's equally pressing up, and if you want you can put them in. Okay, let's see how that works out. Sum of forces in the y direction is 0. That's what I'm going to use. That means 0 is, let me write it formally down, pressure over an area width times dx. W goes in that direction, also the third direction, at position here at the bottom y, and then this is y plus dy, slightly higher. So at the top something is pressing down, and I know that I write this only to sum all forces, because I know that these two, the pressure doesn't change, it's a constant in the system, so these equate to 0. But I got now my forces, so then I need to add a shear stress, x, y, because the velocity is in the y direction and it changes in the x direction. On the left side, that is at position x, and that runs at an area W times that height dy. On the other side, there is a similar force that I need to add. It's slightly displaced at x plus dx, and it's over the same area W times dy, but it carries a minus sign, because of action is minus reaction. It's the big coordinate on the small coordinate, and that is not tau, but minus tau. And then I shouldn't forget that there is obviously gravity, which is rho g times volume is W dx dy, and that should carry a minus sign, because gravity is in the negative y direction, and I use g as a positive constant. Okay, let's take a look. This one is out, W can be taken out, and I'm going to divide the dy's out, and I divide both by dx. Then I get from this, the tau's move to this side, the d tau x y dx, because I divide everything also by dx, and this doesn't contain a dx. Now it does. and that equals what is staying behind, and that is minus rho g. W out, dx and dy taken out. Okay, of that, can integrate this once, that gives me tau x y equals minus rho g x plus an integration constant. Do I know this integration constant? Yes, I can find that, because I can argue that on this side, the air side, so at x equals d, the downward flowing liquid feels a frictional force from the air, but air has hardly any density, low viscosity, so for all practical purposes there is no friction. So I equate this to 0. And thus that c is fixed, and I find that tau xy equals rho g d minus x, which I can draw from the wall towards that. It's 0 here and it starts positive. So this is tau xy. Okay, let's pause for a minute. Do we understand this? It says that liquid here has a positive upwards force on liquid there. That makes sense, because the liquid is coming down at a faster rate, at a faster velocity. If you move outwards, there's less influence of the wall. And thus this liquid flows slow, this flows faster. Slower liquids slows down, pulls up the faster liquids. Exactly what I calculated. So all seems fine. Now that I have that, I invoke that this is a Newtonian fluid, and thus that I can write minus mu d dx of Vy. That is my tau xy, and that is this rho g d minus x. Can simplify this. Minus mu goes to that side, and I integrate. So I get Vy as a function of x is minus rho g mu, that is the minus mu taken. Integrating d is dx, integrating minus x is minus x squared, plus a second integration constant, because I've been integrating. Do I know this integration constant? Sure, I can find it, because I got a boundary condition. At the wall, that is at x equals 0, there is the stick condition for this Newtonian liquid. Vy must be 0, and thus this coefficient C2 is 0. And thus I have that Vx, Vy I mean, as a function of x equals minus rho g over mu dx minus x squared, which is parabola shaped, and I can draw that from wall to air. Now I'm going to draw Vy. At x equals 0, it is 0, it starts here. I put it in myself. Then if x increases, first this term increases faster for small x than that one, so this is positive for small x, and the entire thing starts negative, and it moves something like this. It's a parabola that has its maximum here. How do I know? So this is the velocity downward. How do I know that it has its maximum here? Well, I can just inspect it and find the extremum, minimum of maximum of this function, and you will find that it's sitting at x is d. But I already computed that. To find the minimum or the maximum of Vy, I take its derivative. Well, I got its derivative. If you ignore the minus mu and set that derivative, which is tau then, equal to 0, yeah, that's at x is d. So the derivative here is 0 because tau is there 0. This really ends with a horizontal curve. Now you got an example where gravity is moving everything downward.